So I do see.
First, are there any questions or concerns? Any questions or concerns? So today we want to go over the appendicular skeleton, which is lab exercise 9. And then I want to spend the rest of the time getting caught up a little bit on chapter 12 in the lecture. There any questions? Everyone's not saying anything so far.
No.
So the appendicular skeleton includes the hip girdle and the pelvic girdle and the upper limbs and lower limbs. So the pectoral girdle includes the clavicle, the scapula, and the humerus. Looking at the clavicle itself, it has a sternal end and an acromial end. The sternal end is going to articulate with the sternum. And the acromial end is going to articulate with the acromion process of the scapula. And the head of the humerus is going to articulate with the glenoid cavity of the scapula. So looking at the scapula itself, let's look at the posterior view first. Posterior view has a spine. You can feel it on what we'd call someone's shoulder blade. Can feel it moving all the way up the back. The acromion process, coracoid process. Acromion meaning the highest point. Coracoid meaning like a crow's beak. Has a medial border, which is the border that's going to be closest to the vertebral column. Give me 1 second. So looking at my intact skeleton. Medial border, lateral border, the spine, the acromion process, the coracoid process towards the front, coracoid process. When looking specifically at the spine, you have the infraspinatus fossa, meaning the valley that's underneath the spine, the supraspinatus fossa. Up here, you can't really see it on the back, but you can see it on the front. There's a suprascapular notch, also called just the scapular notch. On the inside, toward the anterior surface of the scapula, there's a subscapular fossa. So just kind of repeating again here. Sternal end of the clavicle, acromial end of the clavicle that articulates with the acromion process of the scapula, the spine of the scapula, infraspinatus fossa, supraspinatus fossa, medial border, lateral border. The head of the humerus is going to articulate with the glenoid fossa. Any questions about this? Looking at the humerus, the head, looking at the anterior view, the intertubercular groove, the lesser tubercle, the greater tubercle. Lesser tubercle meaning more towards the front. Lesser tubercle, greater tubercle. The head, right underneath the head or right immediately inferior to the head, is the anatomical neck, because this would be the neck right underneath the head. The humerus also has a surgical neck, because this is the place where the humerus is most likely to get broken. It's not going to get broken along the anatomical neck. It's going to get broken along the surgical neck, which is much more exposed. Looking at the posterior or the distal end, there's a capitulum. It's a looks like the dome of a Capitol building. So it's a capitulum. Is it trochlea? Trochlea means like a spool of thread. The lateral epicondyle, the medial epicondyle, the radial fossa is going to articulate with the head of the radius. The coronoid fossa is going to articulate with the coronoid process of the ulna. The olecranian fossa is going to articulate with the olecranian process of the ulna. For a moment. So, Mom, would you grab me a pen really quick? Please. Would you open the back room too?
See if it works. It's open.
I don't need it to work. I just need a pointer.
Oh,
Would you open the back door so she just sit there and meow at the door?
it's open.
Is it? Why is he meowing? I don't know. So, lesser tubercle, greater tubercle, the head, the anatomical neck, the surgical neck, the intertubercular fossa or intertubercular groove. I think that's also what it's called. Looking at the distal end, the radial fossa, the coronoid fossa, the lateral epicondyle, the medial epicondyle, the head of the radius, when it flexes is going to move into the radial fossa. The coronoid process is going to articulate of the ulna here. It's going to articulate into the coronoid fossa. Looking at the back, the olecranian process, which is essentially your elbow, is going to articulate into the olecranian fossa. Questions? So a lot of things are named according to what they're located next to, what they articulate with. So the coronoid fossa articulating with the coronoid process. The radial fossa articulating with the head of the radius. The chromian fossa, the olecranian fossa articulating with the olecranian process. The trochlea is going to articulate with the trochlear notch in the ulna. Looking at the humerus, the radius in the ulna. The radius is on that. If you look at the anatomical position, Do you remember what anatomical position is? Someone describe to me anatomical position.
From the front view,
You're facing the front,
Palms are facing towards the front.
palms are facing towards the front.
feet planted on the ground with toes facing forward.
Yep, feet planted on the ground with toes facing forward. What's going on with the head?
It's looking forward.
It's looking forward with the head, with the chin up. What about, I think that's about it. So if the palms are facing forward, what bone is on the outer of the ulna and the radius and the ulna? What bone is facing towards the outer edge? What bone is at the outer edge? The radius or the ulna?
Radius.
The radius. How do you remember that? How do you remember that it's the humerus and the radius is on the outer edge? A way that I tend to remember it is I remember that the radius is right up from the thumb. The ulna is right up from the pinky. Another way to remember it, another way to remember it is to remember that the radius is going to be, if you think of the radius as the outer edge of a circle, from the distance in the center to the outer edge, the radius is on the outer edge.
Isn't one bigger from the other?
What? It kind of is, but it really isn't. It looks like it is, but it's not. They're about the same. The radius may be a little smaller, but they're about the same.
Okay.
It's a good, yeah, that's a good idea. They might be a little bit, but it's a little negligible. The way that I can remember that this is the ulna versus this is a radius is the ulna, and I wish I had a single ulna bone to just show you, but the ulna has a U right here. It makes a U at the very top here.
Yeah, because I just kind of looked at the shape.
Yeah. Oh, that's okay. I understand, and Michaela, it does kind of it could be a little bigger, maybe. I'm just not sure. I would say the one thing that you can tell is the most proximal, the proximal end of the ulna, this end. If you look at it in another direction, ulna, this. Let's see. Oh, if we're gonna find one. All right. Looking at so if you look here, right here, this is the proximal end of the ulna. It has a U right there. Looking at head of the radius. Here's the head of the radius. It makes a full circle on the top of it. So the U, ulna has a U. The head of the radius it looks like a circle.
Okay.
At the distal end, two other things. There's a radial tuberosity on the radius where it articulates with the ulna. The styloid process of the radius looks like a sharp point. Kind of see it on my, still it's in here. At the very bottom, there's a sharp point on the radius. There's a sharp point on the ulna on the other side. Styloid meaning like a stylus, something you can write with. So you could think of it as being like something that you would maybe dip in a well of ink and write with. So the styloid process of the radius, the styloid process of the ulna. Looking more at the elbow joint itself, the capitulum, the trochlea, which is going to articulate with the trochlear notch of the ulna, the medial epicondyle, lateral epicondyle, the head of the radius, which articulates with the capitulum and is going to move into the radial fossa. Coronoid fossa is going to articulate with the coronoid process. The trochlea is going to articulate with the trochlear notch. Lateral epicondyle on the radius. The the medial epicondyle. One other thing that I will show you here is an experiment. Do it only on yourself. Don't do it on someone else. But if you, so here's my olecranian. Here. I can feel the medial the lateral epicondyle right here, and the medial epicondyle right here. Right in between the olecranian and the medial epicondyle, there's a little indentation right there. And do me a favor, take that part of your elbow right now and slam it really hard on a desk. Okay, maybe you shouldn't do that. What happens when you've ever accidentally done that?
It hurts and
Why
it's
does
tingly.
Why does it hurt and tingle?
Isn't there a nerve right there?
There is, Rachel, there is. If you, so don't slam it down, but right now, right in there, put pressure right there. Pressure right there. And you got to push kind of hard. That's why I'm saying don't do it to someone else unless you're really careful. And where do you feel the tingling? Where do you feel it?
Down your arm.
What part of your arm?
Radius.
Is
Like
it the
down
is it the radius or is it the ulna?
I mean, I'm feeling it on my thumb side, so maybe I'm not doing it right.
Okay, do the other side. Do the other side. So here's my pinky. Do the other, do the side where the pink of where the pinky is gonna be. Where do you feel it?
The pinky side.
The pinky side, because your ulnar nerve is right here. And what happens when you hit that is it's essentially crushing that nerve up against the bone. What have we nicknamed that?
The funny bone.
The funny bone. It's really not very funny when you hit it though, is it?
No, but you gotta laugh
You have
so
to
you don't
laugh
cry.
or you'll cry. That's true. You gotta laugh or you'll cry. But yes, on a cadaver, that nerve, let's see if I can find a picture of it. That nerve is highly exposed. It's big and it's exposed. And let's see. Medial epicondyle. See if I can find a cadaver view. It's highly exposed. It's huge. Here's the medial epicondyle. Here's the lower cranium. It's a big nerve and it's very, very much exposed. So what happens when you bang it is you're banging it, you're crushing it up against the bone. And that's why it tingles.
We're not seeing anything if you're trying to show us
Oh,
something.
shoot. Yep, I am. You see it now?
Yes.
So it's right here. Here's the medial epicondyle. Here's the olecranian process. And here's the ulnar nerve. So it's highly exposed. It's really easy to dissect out. It's very much exposed. So moving forward to the hand. The hand has, the fingers are made of phalanges. All you want to remember is that there's 3 sets of phalanges. Proximal, the middle, and the distal phalanges. On the thumb, there's only 2 phalanges. These bones right here are the metacarpals. Because they're in between the phalanges and the carpals. Looking at the wrist, the best way that I can remember the bones on the wrist is through mnemonics. So the one that I like best for the wrist, and there's a lot of different mnemonics. If you go on and you look for mnemonics for learning the carpals and Google that, you will find lots and lots of stuff. The one that I remember the best is some lovers try positions that they can't handle. So so for the bones involved here, looking at the wrist, some scaphoid lovers lunate triquetrium positions pisiform, that trapezium, they trapezoid can't capitate handle hamate. So scaphoid, lunate, triquetrium, pisiform, trapezium, trapezoid, capitate, hamate. You don't see it really well here, and I don't think it's really well on my little tiny skeleton. Oh, it kind of is. Let me see. If you look, here's the wrist, and right on that outer edge, right next to here's the thumb, right on the outer edge, right here where my finger is, there's a little hook. It's a little hook. That's the hamate. On the other side, there's a little like P-shaped bone right here. That's the pisiform. So some lovers try positions that they can't handle. Scaphoid, lunate, triquetrium, pisiform, trapezium, trapezoid, capitate, and hamate. So some lovers try positions that they can't handle. So some is scaphoid. Lunate. Triquetrium. Pisiform. Trapezium. trapezoid, capitate, handle, hamate. Like I said, I try to orient myself either with the hook on the hamate or the pisiform, the pea-sized bone. Questions about the wrist? If you're familiar with carpal tunnel syndrome, there is a tendon that wraps around the arm right here. And I can't remember exactly what it's called. I think it makes a tunnel and the median nerve runs through it. And when that tendon gets inflamed, it swells and the median nerve gets inflamed. So the numbness that you can feel with carpal tunnel syndrome is essentially the pinching of that median nerve underneath that tunnel. So what they tend to do when they treat carpal tunnel is they'll go in and make small cuts in that ligament to kind of give the median nerve a little bit more room. My dad is a big computer person, and he has had surgery on his carpal tunnel at least 3 or 4 times on each of his wrists. Any questions? Moving on to the pelvis, 3 bones make up each side of the pelvis. We also call the pelvis what's called the os coxae. Os coxae. So 1/2 of the pelvis is called the os coxae. So this is 1/2, this is 1/2, and they articulate with the sacrum. Each os coxae is made of 1 pubis bone, 1 ischium, and 1 ilium. The end on the back of the ilium is going to articulate with the sacrum. In the front, the pubic symphysis is where the 2 pubic bones of each os coxae come together. Symphysis meaning coming together or joining. And there's some fibrocartilage right here. This is a joint that's made to be able to move out and twist a little bit to allow for a baby to move through this pelvic canal. looking at the side views, the medial and the lateral views of each os coxae. Here's the post anterior surface. So this is this surface right here. Here's the posterior surface. So where the pubic symphysis is going to meet up with the other pubic bone. You can feel the iliac crest on most people, or lots of people. Second here. Oh, baby. So on a given person, right here, and then if you move your fingers back, you can feel the iliac crest. The anterior superior iliac spine right here. Then you move it back and you can feel the iliac crest moving all the way across the top. So here's the anterior superior iliac spine, which you can often feel. The iliac crest runs all the way back to the posterior superior iliac spine, which you can often feel on people too. If there's an anterior superior iliac spine, there's an anterior inferior iliac spine. If there's a posterior superior iliac spine, there's a posterior inferior iliac spine. There's a greater sciatic notch. Do you know anyone who's ever struggled with sciatica?
No, what is that?
It is where their sciatic nerve is being pinched. It's a major nerve, and when we talk about the spinal cord, which is coming up, it's a major nerve that's coming off the lumbar plexus and the sacral plexus, and it's being pinched. And then what it does is it sends numbness down the back of their leg. It is coming through right here, the greater sciatic notch. Let me see here. And greater sciatic notch. Right here's the sciatic nerve. We don't see it right here, but right in this little indentation right here is the greater sciatic notch. This right here is the posterior superior iliac spine. It's covered by this ligament, but the posterior inferior iliac spine. See if we can see it a little better here. Not really. That was a better view before. So it's essentially, it's a pinching of that nerve. So the greater sciatic notch, the lesser sciatic notch. The ischial spine is essentially it's the bone that people sit on. If you've ever had someone sit in your lap and they have a bony butt, that's what you're feeling is the ischial spine. Ischial tuberosity. The pubis bone. The acetabulum is where the head of the femur is going to articulate with the os coccyx. Acetabulum. Inferior ramus, pubic ramus. Superior ramus of the pubis. Ischial ramus. Remember, a ramus is an arm. Obturator foramen. Foramen, remember that's a hole. There's a nerve called the obturator nerve, which is going to come through here. The obturator foramen. So looking at these views, here's your obturator foramen. Here's your acetabulum. Here's the anterior inferior iliac spine. It's the anterior superior iliac spine. Posterior superior iliac spine and the posterior inferior iliac spine are going to articulate with the sacrum. Back here. Questions? The head of the femur. Or the femur itself. Here's the head of the femur. Remember, we had a head of the humerus, so it looks very similar in a lot of ways. Here's the head of the humerus. Here's the head of the femur. Right in the center of the head of the femur is the fovea capitis. Right here. Right here. This is where the femoral nerve and artery, actually not the femoral artery, but a femoral nerve is going to come through. Looking at the anterior view of the femur, the greater trochanter, the lesser trochanter. Here's an intertrochanteric line, so a line in between the greater trochanter and the lesser, the lesser trochanter and the greater trochanter. Right in between the intertrochanteric line and the head of the femur is the neck. The medial epicondyle, the lateral epicondyle, down to the bottom. Just like you see on the humerus, the medial epicondyle and the lateral epicondyle. The medial condyle, epi meaning right above another condyle, and the lateral condyle over on this surface. Patellar groove, where the patella is going to sit. Patella meaning your kneecap. And at the posterior view, the head, the neck, the greater trochanter, the lesser trochanter, the intertrochanteric line or crest. The gluteal tuberosity is where the gluteus maximus is going to insert. Gluteus maximus is essentially the muscle of your butt. The big muscle that makes up your buttocks. Your linea aspera. Big line that runs down the back on the femur. The lateral epicondyle, and the medial epicondyle, the lateral condyle, and the medial condyle, and the intercondylar fossa in between, meaning in between the two condyles. Questions? So looking at the knee articulation, the medial condyle of the femur, the lateral condyle of the femur, the patella, the tibia, and the fibula. On the anterior view of the tibia and the fibula, the lateral condyle of the tibia, the medial condyle, let me see here. Yeah, lateral condyle of the tibia, medial condyle of the tibia. The anterior border, this is your shin. Anterior border. The medial malleolus and the lateral malleolus be over here. These are your two bones that you feel on your lower leg. Here's my tibia. Medial malleolus, lateral malleolus. The anterior border of the tibia. The tibial tuberosity. Articulates with the lateral condyle, the medial condyle. Articulates with the lateral condyle of the tibia and the medial condyle of the tibia. Any questions? So the ankle articulation, here's your lateral, excuse me, your lateral malleolus, your medial malleolus, calcaneus. Remember, this is the strongest bone in your body. Why do you think it's the strongest bone in your body, this calcaneus right here?
Because you put your most weight on it.
Yeah, you're constantly putting weight on it. You're constantly putting weight on it. And if you remember Wolf's law of bone, the more weight, mechanical force and tension you put on a bone, the stronger it becomes.
I thought her teeth were the strongest bones.
Your enamel is the strongest, but your enamel technically isn't bone.
I thought the femur was the strongest.
Your calcaneus is the strongest. Let's do something really quick. You can actually break a femur pretty easily. Let me not really easily, but strongest bone in the body. Says the femur. They say that, all right, why is it saying that? You know what, it's saying that, but I can tell you that you're less likely to break your calcaneus than you are to break your femur. Because they say the hardest bone in the human body is the jawbone, but I can tell you that's easily broken. Which bone is the strongest? Okay, I'm getting my analogy ruined here. The hardest bone to break. Let's not go this way. I don't want to go this way. Bone to break. Still saying your femur. Let me come into all. It's still saying that that's the hardest one to break. And I know lots of people who have broken their femur. Bear with me just for a second. Because all the evidence here is going against what I'm saying. Okay, never mind. I keep being told that it's the hardest bone, but it doesn't seem to be the hardest bone. But I would say that when you want to consider bone remodeling, that would be your toughest bone. I need to quit saying that it's the strongest bone in the body. If they're telling me it's a femur, but I know lots of people who have broken their femur. If you think about it, people that you know who have broken their femur, do you know people who have had to have a hip replacement or they break a hip?
Yeah.
That's a break of the femur. How often have you heard of that?
Kind of like not often, but like kind of often. Like it's
Right.
not something.
It doesn't, it doesn't happen all the time. But when people break their hips, you hear a lot about people falling, older people falling and breaking their hips. That's their femur. They're breaking the neck of the femur. So I'll quit saying that the calcaneus is the hardest bone. But when it comes to Wolff's Law bone, it is the hardest bone because you're constantly putting weight on it. It's not the biggest bone, but it's the hardest. Looking at the foot, here's the calcaneus, the talus, the navicular, the cuboid. On the opposite side here is the medial cuneiform, the intermediate cuneiform, and the lateral cuneiform. Another way to remember these, like I said, my best way to remember the bones of the carpals and the tarsals are mnemonics. So this one is tiger cubs need milk. Tiger cubs need milk. L. And milk spelled with a C. So talus, calcaneus, navicular, medial cuneiform, intermediate cuneiform, lateral cuneiform, cuboid. Calcaneus, talus, tiger, cubs, need, navicular, milk, medial cuneiform, intermediate cuneiform, lateral cuneiform, cuboid, tiger, cubs, need, milk, medial, intermediate, lateral, cuboid. Then the metatarsals and the phalanges. And just like your thumb, your big toe only has 2 phalanges in it, while the others have 3. Talus, calcaneus, navicular, medial, cuneiform, intermediate cuneiform, and cuboid. One thing that helps to orient here, either orient yourself by the calcaneus, or another way that I orient myself is with the navicular, because the navicular looks like a boat. It's like a little bit of a boat. Or the cuboid looks like a cube-like shape bone. Or the medial cuneiform is right proximal to the big toe. Any questions? You guys, let's take 10 minutes and come back and work on lecture just for a little bit. So come back at 10:52.
Professor, I just wanted to double check some due dates.
Okay,
Sorry, I've been moving the last
I know, I saw your email.
yeah, I apologize. It's
You're okay.
a little, I think I bit off more than I could chew. So for chapter 12, is that all due the 7th, the smart book, the
I think that's a good idea. I may
Okay.
extend it out.
okay, I'll just put the 7th for now. And then chapter 13, we haven't started yet, correct?
We haven't started yet.
Okay, cool. I just wanted to
We
make sure.
we will start it next week. We'll work on chapter 12 for a little bit today, and we will start chapter 13 next week.
Okay. And then, so chapter 12, chapter 13, Lab Quest 3, it says it's late on the McGraw Hill, but did we extend that
Let
one?
me extend it out right now.
Okay, sorry, I just saw
No,
all the due dates and
it's
started
okay.
freaking out this morning.
Okay, it's okay.
Thank you. Yeah, me too.
Yeah, I know we talk about it in class. I've just been like so preoccupied that I've been having trouble keeping tabs of all the dates. And I couldn't find the notebook that I usually use, like
Yeah.
paper notebook. So I feel very lost currently.
I understand that. So the smart book assignment says it's due November 10th
Okay.
for
For
chapter
12.
12.
Okay.
Let's see here. It's 3.
Okay.
Put this out a little bit further. Let's make this due next week. The 3rd.
Oh, and then the case study is due.
It's due in 2 weeks, so it's due on the 10th.
Okay. Case study is due the 10th. And then
Did I never assign the chapter 12 quiz? Shoot.
yeah, I only saw the smart book in the
Let
practice.
me look at it just for a quick moment. I'll stop that. No, go back. Go back.
And then
Give me one
I'll
second.
wait
I'm
until
sorry,
you're-
Terry.
yeah, sorry.
It's okay. One moment. I just want to make sure it's set up the way I want it to be. Yeah. Review and assign. Okay, now it's on there.
Okay. And the last thing would just be the 3 muscle labs are still due the 10th, correct?
The bone labs.
Okay.
Yes.
Okay, cool. I just wanted to write everything down.
Oh, the virtual muscle labs. They, you know what, I will, this is what you're referring to, the virtual labs.
I believe, yes, yeah, those
I
three.
will extend those out. We
Okay.
haven't even covered that yet.
Okay,
I will extend those out. They'll actually be due towards the very end of the semester.
okay.
Do that right now. I'm gonna have them do the 1st of December. More. Um, Okay, I'm gonna do one other thing here while I'm at it, and I'm saying it. The nervous system, the monosynaptic reflexes.
Yeah, I was just about to ask about that one too.
Yeah, I'm gonna have that one due actually on the 10th of November because we'll do that lab next week.
Okay. And then is LabQuest 3 on lab exercises 8, 9, and 10?
I think so.
Okay.
And it's over one other one, I think.
Okay.
I have to go back and look.
Sorry, I know I'm like asking you 20
No,
questions.
it's okay. I made up that LabQuest 3 like maybe 3 weeks ago. And so I have to remember what it's covering. Terry, you just keep me on my toes. Give me a moment here. Let me.
Well, I know you have quite a few classes to juggle and like.
Well, but you know, I just have to remember. So let me look at the syllabus and then I can tell you. It's covering the integumentary system too.
Okay, so 7 through 10.
Yeah.
Cool.
All right. I'm gonna get up and walk away from my computer just for a minute longer.
Okay.
And I'll
Sorry
come
about
back.
that. Sorry.
No, you're fine. No, this is good. Thank you. I'll be right back.
Thanks.
Do you think you need to go out? Yeah, you need to go out. Says I'm on the couch here, Mom. I can't get off. Call her now. Paisley, come here. Yeah, come on. Girl. What did your students think? Or did you show them? They paid attention a little bit. But trying to get from the voices. Our little 3-year-old trying to pose. I don't believe we were all the way there. Let's start at 70. We'll start. Let's skip up to right here. So coming to back, looking at the nervous system. So we talked about the resting membrane potential. There's three kinds of gated channels that maintain the resting membrane potential and that are involved in the movement of ions. These types of channels open and close in response to different stimuli. They give nerves and muscle cell membranes the properties of excitability. So they can open and close in response to a chemical stimulus, a ligand binding to something, a part of the channel opens or closes the channel. A mechanical push, something bumps the channel and it opens. Or a change in the voltage that is going to open the channel. For example, the channel is open at minus 70 millivolts and starts to close at minus 50. Or it's actually, I'm sorry, I'm looking at the picture a little wrong here. Minus 70 is closed, at minus 50 it's open. Ligand-gated channels open and close in response to specific chemicals. Some chemical ligands include neurotransmitters, hormones, and ions. Many are concentrated, many of these types of channels are concentrated at the synapse. Remember the synapse, if you think of a synapse as being like a snap, where one cell is going to come in and join with or be in conjunction with another cell. These are very numerous at the synapse, numerous at dendrites, and the cell bodies of interneurons and motor neurons. Mechanically gated channels are going to close or open in response to a mechanical pressure or vibration. They get bumped and they open. The pressure drops and they close. These are found in hearing receptors, stretch receptors, and touch receptors. So they're responding in response to pressure on the receptor. Voltage-gated channels are going to open in response to changes in the membrane potential or close in response to changes in the membrane potential. These type of channels are going to participate in the generation and conduction of action potentials, which we'll talk about in a couple minutes here. They're mainly located along the neuronal axons. So neurons are going to communicate by using two types of electrical signals. Graded potentials are short distance only. Action potentials are going to communicate over long distances. two types of electrical signals, graded potentials or action potentials. Which potential grade travels the greatest distance? As you touch a pen, a potential is, a graded potential is fired via the sensory receptors in your fingers. Once the inner neurons in the cerebral cortex in the brain are activated, perception of that pen, being able to feel that pen, results in being able to feel the surface of the pen. So graded or local potentials are changes in the resting membrane potential that are occurring nearby or close to where they were first stimulated, where the membrane was first stimulated. Graded potentials can vary in magnitude according to the strength of the stimulus. A longer, stronger stimulus is going to result in a potential of a larger magnitude. Graded potentials are decremental, meaning that they get weaker as they spread away from the point of origin. They also can summate. So two potentials can be added together to result in a bigger potential being produced. One positive potential change and one negative potential change can neutralize one another in contrast. They're also reversible. Once the stimulus ceases, whatever started the potential change ceases, the diffusion stops, and the different things that are involved in maintaining the resting membrane potential return the resting membrane potential back to where it normally is. Remember, we talked about what those things were, like the sodium potassium pump and the leak channels for sodium and potassium, and the negative ions within the cell membrane that are stuck within the cell. These graded potentials can also be excitatory or inhibitory, which means that they can either excite a membrane potential or they can cause further inhibition of other potentials. By hyperpolarizing or depolarizing the membrane. So graded potentials mean that a membrane potential can vary in its amplitude. The greater the stimulus strength, the larger the amplitude of the graded potential.
Okay, teaching assistant.
Let me see my teaching assistant back. You've met the teaching assistant, right? Let me see here, just a second. Let me stop sharing for a moment. I think you've met the teaching assistant.
I think we have.
Okay, good.
Yeah, we have.
Yeah. I always, as soon as my class gets ready to start, I'm like, come on, we need to go teach. Come on. Oh, yeah. She gets very excited and then she falls asleep during the lesson. Just like my mother, that's terrible. She said, when I said she falls asleep during the lesson, my mom says, just like your students, mother, go find somewhere else to be. Okay. So the greater the stimulus strength, the larger the amplitude of the graded potential. A more prolonged, more intense stimulus is going to result in more gated ion channels being open for a longer time. The result is that more sodium will be able to enter the cell. Remember, sodium is more concentrated on the outside than the inside. So more sodium will be able to enter the cell. If more sodium enters a cell, the membrane potential is going to become more positive. It's going to go from being minus 70 millivolts to maybe like minus 50 millivolts. This relationship between a stimulus strength and the amplitude can also cause a more and stronger inhibitory or hyperpolarizing potential. So they can add together, and a larger stimulus is going to open more ligand gated channels, and more ions are going to flow across the plasma membrane. They can sum together, so they're voltage variable amplitudes that can be added together or cancel each other out. The net result is that you get a smaller or larger graded potential. And because they can die out within a few millimeters of their origin, they're decremental. So graded potentials are useful for short distances only. If two depolarizing, remember depolarizing meaning the membrane becomes more positive. Remember, the greater the membrane potential, the more negative it is. The more negative the inside is. So if something becomes less polar, like becomes depolarized, it's going to become more positive inside the cell. The net result is a larger depolarizing graded potential. A depolarizing graded potential is a stimulus that's going to cause a reduction in the difference of charge, making the cell become less negatively charged with regards to the outside. Becomes less negatively charged, goes from a minus 70 to a minus 60. Hyperpolarizing graded potential is when the inside of the cell becomes more negatively charged with respect to the extracellular fluid. So depolarizing meaning it gets closer to the charge on the in the extracellular fluid. Hyperpolarizing meaning the charge difference between the outside and the inside of the cell becomes even greater. There's a balance between these two types of potentials. So how a neuron, and this allows a neuron to be able to process many different inputs, many different potentials. The summation of them allows for being able to make decisions about many incoming inputs of information. Some examples of hyperpolarizing and depolarizing graded potentials. Acetylcholine is a neurotransmitter that usually causes depolarization, so causes the membrane potential to become more positive, going from a -70 to a -60, with more sodium entering the cell. The cell's membrane becomes more positive, so it is more likely to reach threshold and fire an action potential. We'll talk about how that works here in a second. Glycine causes the inside of the cell membrane to become more negative, meaning making it less likely to fire an action potential. So glycine causes a hyperpolarization of the membrane, making it even more negative than it was to start out with. So most graded potentials are going to occur in the dendrites and the cell bodies, and they don't travel down the axon. Questions? So graded potentials occur as the result of opening or closing mechanical and or ligand gated channels. Whether the membrane potential becomes more positive, meaning it gets depolarized. Let's do this real quick, because this is going to be important here in a moment. If the membrane potential becomes a depolarizing membrane potential, means that the membrane potential, the difference between the outside of the cell, the charge on the outside of the cell and the charge on the inside of the cell, is going to decrease. So potential is going to decrease. If you remember, polarizing meaning that there's a separation in charge. So if it gets depolarized, there's going to be a reduction in that separation of charge. So the potential becomes more positive. Hyperpolarizing is because the membrane potential becomes more negative, meaning it makes it even more polar than it was before. The separation charge becomes even more than it was before. Depolarizing is usually caused by sodium entering the cell, because that's going to result in the cell inside of the cell becoming more positive. Remember that the outside of the cell contains much more sodium. There's a lot more sodium outside of the cell than inside of the cell. Sodium entering the cell. When things get hyperpolarized, meaning it becomes more negative inside the cell, it's because potassium either leaves the cell, remember how potassium is much greater inside the cell than it is outside. So if you ever open the channels for potassium, it's going to leave the cell, because things always move from a high to a low. It's going to leave the cell. Also, another thing that can happen here is chloride can enter the cell and make it more negative. Questions? Chloride is the balancer for sodium on the outside of the cell. So there's more chloride outside of the cell than there is inside. So if we open channels to allow chloride to flow, it's going to move into the cell, because things always move from a high to a low. So which type of action potential is not going to decay with distance? And you know what, we haven't really, I should put this question somewhere else. This isn't really the right place for this one. It's the action potential. Not going to decay with distance. The graded potential will. So action potentials are what occur when there's a nerve fires a signal. So an action potential is a dramatic change produced by a voltage-gated ion channel in the plasma membrane. These only occur when there is enough of voltage-gated channels. If you remember when we were looking at the general structure of a neuron, here's the soma, here's the dendrites, here's the axon hillock, here's the axon. Right here's the trigger zone. Most of the cell's soma, cell body, has a density of about 75 channels per micrometer squared. The trigger zone has about 300 to 500 channels per micrometer squared. So if action potentials are only going to occur where there's enough of a density of voltage-gated channels, that means they're only going to happen in the trigger zone. Because there isn't enough channels in the soma for that to happen. If a strong enough excitatory local potential that's initiated out here in the dendrites or the soma arrives at the trigger zone, it can open voltage gated channels. Remember how we have channels that can open in response to a change in voltage. So it will open those channels in the trigger zone and generate an action potential. An action potential is a rapid up and down shift in the membrane's potential. So here's our resting membrane potential right here, minus 70. Excitatory or depolarizing membrane potentials are going to make the membrane potential more positive. Inhibitory or hyperpolarizing potentials are going to make the membrane potential more negative. If they sum up to where we have so many positives and only a few negatives, if they sum up to a certain level of positivity of that membrane potential, if it reaches a certain point, then we will initiate an action potential. Questions? So an action potential steadily rising because we have enough excitatory depolarizing potentials that are occurring. Sum up and they at about the area of the trigger zone. And they become, it becomes out at least reaches a negativity. So starting at negative 70 reaches negative 55. This is a threshold. It's negative 55. If the membrane potential reaches this negative 55, this allows for an action potential to occur. So if the local potential rises to this critical depolarization voltage, the threshold of negative 55 millivolts, it's going to open the voltage gated channels and initiate an action potential. If we get lots of little excitatory action potentials, get lots of little high depolarizing channels, but never enough to reach minus 55, no action potential will be initiated. You have to reach the threshold or nothing occurs. So it's an all or nothing. Either you reach this threshold and an action potential is fired, or it never occurs. When the action potential is fired, at this threshold at minus 55, a bunch of voltage gated sodium channels open quickly. So at that threshold of minus 55, this is the threshold needed for a bunch of voltage, sodium gated voltage channels to open. They all open And at the same time, we get some potassium channels that start to open a lot slower. And remember that potassium is going to leave the cell because it's more concentrated inside the cell. And sodium is going to enter the cell because it's more concentrated outside of the cell. And everything moves from a high to a low. So the neuron now produces an action potential with the voltage-gated sodium channels opening quickly, while the voltage-gated potassium channels start to open gradually. Initially, a few sodium channels open, but as more sodium enters a cell, it further depolarizes the cell, causing more sodium channels to open. So this is a positive feedback loop. Remember what a positive feedback loop is. When one change encourages another change, pushing things further from the narrow limit median value where they normally would be. So a positive feedback loop that causes the membrane voltage to rise even more rapidly. So as sodium enters the cell, it becomes more depolarizes, depolarizes, depolarizes. Until we're actually in the positive value where the inside of the cell is more positive than the outside of the cell. As the potential rises past 100 millivolts and peaks at a positive 35 millivolts, meaning that the polarity is completely reversed, the sodium channels are inactivated and begin to close. So once we reach the 35 millivolts, the sodium channels start to close because at that voltage, they start to close. At this point, when the sodium gates start to close, now the potassium channels that started to open at the beginning, but were much slower in their opening, are now fully open. And potassium starts to move out into the extracellular fluid and repolarize the membrane, make it more negative again. Because remember, as sodium is leaving the cell, it's going to make, because it's positively charged, it's going to make the inside of the cell more negative. So the action potential has this rapid up and down motion where the voltage reaches threshold and then returns to resting membrane potential. These potassium channels that were completely open right here tend to stay open longer than the sodium channels do. So slightly more potassium leaves than sodium enters, resulting in a slight hyperpolarization of the membrane, where the membrane becomes a little bit more negative than the resting membrane potential, -70. So maybe it reaches, let's say, -73 rather than just -70. So during this overall action potential, the sodium and potassium are switching places across the membrane. during the hyperpolarization, because sodium gradually diffuses into the cell, is still moving a little bit, the membrane potential gradually will move back to the resting membrane potential. Questions? I'm going to go through this again, maybe a little faster, but I'm going to go through it one more time because this is kind of it's an important process here. So we get a bunch of small depolarizing localized potentials that are occurring within the soma of the neuron. If enough of them are occurring and they summate so that at the axon hillock or the trigger zone, the membrane potential reaches this negative 55. This is the threshold. And at this threshold value, sodium gates start to open. Lots of them start to open. At the same time, potassium gates are slowly opening, but they're not opening as fast as the sodium gates are. With this opening of all these sodium gates, this is where the neuron produces an action potential. And the voltage gated sodium channels are opening quickly while the potassium gates are just opening very slowly. As a few of these sodium gates open, sodium enters the cell and it further depolarizes the cell, causing more gates to open at negative 55 millivolts. So this is a positive feedback loop of where some sodium gates open and they cause more sodium gates to open. Right here. As the potential rises past 0 millivolts, it's going to peak at positive 35. So now the polarity has been reversed. Once you pass the 0 point, things have been reversed. Now the inside of the cell is more positive than the outside of the cell. And at this point, at plus 35 millivolts, the sodium gate channels that were caused to be opened at minus 55 are now closing, because this is the voltage at which they close. At this same time that the sodium gate channels are closing, the potassium channels are now fully open. And the potassium moves out into the extracellular fluid and repolarizes the membrane, causing the voltage to become much more negative again. So the voltage reaches the threshold and then it returns to the resting membrane potential. The potassium channels stay open longer than the sodium channels. So more potassium leaves the cell than enters. Sodium enters. And the result is that the original resting membrane potential becomes slightly hyperpolarized. So rather than just becoming a minus 70, it goes down even a little further because there's still potassium coming in. Still more potassium leaving the cell. During this action potential, the sodium and potassium are switching places. And during the hyperpolarization, sodium was gradually going to diffuse into the cell, resulting in the membrane voltage slowly returning back to the resting membrane potential of minus 70 millivolts. Questions? So there's an interchange here of sodium and potassium channels opening and closing. That's the key. So at the resting membrane potential, both the sodium and potassium channels are closed. When the threshold is reached, sodium channels start to open rapidly and potassium channels begin to open, but they're not as fast. So this is when depolarization starts to occur. Once there's a peak at about plus 35 millivolts in the membrane potential, the sodium channels are going to close at that voltage. And now the potassium channels are completely open and more so potassium is moving out of the cell, causing the cell membrane to become more negative, causing repolarization of the membrane. When the repolarization is complete, the sodium channels are closed and the potassium channels are closing also. Spend some time thinking through this process. This is really important. One of the major parts of this whole entire chapter. Let me ask some questions. What is threshold?
If something reaches a threshold, then it creates an active, I can't remember the word, I'm sorry.
Action potential, yes. So it's going to create an action potential. What happens at that point?
Depolarization.
Depolarization. Why does it depolarize?
Oof. I don't know.
It's going to depolarize because sodium channels are opening and sodium is leaking into the cell,
Okay.
making it more and more positive inside the cell. What's happening with the potassium channels? They're opening, but they're opening a lot slower. During the depolarization, the sodium channels are opening and, sorry, I got a hair in my mouth. As the sodium channels are opening, they're opening more sodium channels. So this is our positive feedback loop. They're opening more channels. And the potassium gates are slowly opening. At the plus 35 during at the peak of 35 or 30, somewhere in there, repolarization is going to occur because at 35, positive 35 millivolts, the sodium gates are going to start to close. This is their voltage at which they close. And now the potassium gates that started to open here are fully open. And so now, because potassium is much higher inside of the cell than outside of the cell, potassium is now leaking out of the cell. And it's moving pretty fast because there's a lot of channels opening, causing the membrane for the inside of the cell to become more negative again. So this is where it gets repolarized. If you think about this depolarization, meaning you were letting charge flow. Repolarization, meaning we're creating the separation in charge again. And hyperpolarization, meaning we're creating a greater separation in charge than we had before. Questions? So action potentials follow this all or none law. If a stimulus depolarizes the membrane enough to reach threshold, an action potential is fired at its maximum voltage of positive 35 millivolts. However, if the depolarization threshold is never reached, no action potential will be generated at all. So if it happens, it's always going to reach positive 35 millivolts. If the depolarization threshold is never reached, no action potential will be generated at all. A stronger stimulus that results in a depolarization above threshold will not create a stronger action potential. The action potential is the same strength every time it's fired, regardless of the strength of the local potentials that initiated it. Once threshold is reached, everything happens or nothing happens if threshold isn't reached. Sometimes I think of this as a ship flying away. So the space shuttle flying, taking off. They have all these checks. Is this okay? Yes. Is this okay? Check. Is this okay? Check. Is this okay? Check. Well, this isn't okay, so we don't go at all. But once we leave, we leave. Action potentials are also non-decremental, meaning they don't get weaker with distance. Remember, local potentials get weaker with distance. Action potentials are non-decremental, meaning they don't get weaker with distance. An action potential at the end of the axon is not weaker than one at the axon next to the trigger zone. It's always the same. It's always the same, always reaches positive 35 millivolts once it's initiated. And action potentials are irreversible. If the neuron's membrane reaches threshold, the action potential will always go to completion. So they either happen or they don't. They don't get weaker with distance. And once they occur, they go to completion every time. After an action potential is initiated, it's very difficult to stimulate or impossible to stimulate that region of that neuron for a few milliseconds in order to initiate another action potential. There's a waiting period. You can't, it's either very difficult or impossible to stimulate a next action potential right then. It's impossible to initiate another action potential during this time when the sodium gates are still open. So when the sodium gates are still open, until they're completely closed, you cannot start another action potential at that moment. This is the absolute refractory period. The relative refractory period is when a new action potential can be triggered, but only by an exceptionally strong stimulus. This is because of hyperpolarization. Remember that the membrane potential is more negative than it was before. So it's even going to be a little harder to reach threshold again. But a strong enough stimulus can do it. So the absolute refractory period is when the sodium gates are still open. Until they're fully closed, you can't initiate another action potential remember how the action potential is initiated by the opening of the sodium gates. So until they're completely closed, you can't reopen them. With the relative refractory period, it's because the membrane is more negative than it would be at the normal resting membrane potential. And so you have to have a stronger than normal stimulus to reach threshold because we're starting at a more negative membrane potential. Questions? So comparison and contrast of local potentials and action potentials. Remember, graded potentials are the same thing as local potentials. So a local potential is produced by gated channels on the dendrites or somas. An action potential is triggered by voltage gated channels on the trigger zone or axon. A local potential may be a depolarizing or hyperpolarizing voltage change. An action potential is always depolarizing. It's always going to make the membrane more positive. A local potential is graded, meaning it's proportional to the stimulus strength. An action potential is all or none. either the action potential occurs and it goes to maximum, or it doesn't occur at all, regardless of what the initial stimulus strength was. It's always going to go to completion. The local potential is reversible, meaning it returns to the resting membrane potential. If the stimulus ceases before the threshold is reached for an action potential. The action potential is irreversible, meaning it goes to completion once it begins, every time. The local potential has effects for only a short distance from the point of origin. The action potential is self-propagating, meaning it continues and continues and continues and has effects over a great distance from the point of origin. So the local potential continues and continues and continues. It self-propagates itself. A local potential is decremental, meaning that the signal gets weaker with distance. An action potential is non-decremental, meaning that the signal maintains the same strength regardless of the distance. Maintenance of the resting membrane potential is possible due to what? What allows for maintaining the resting membrane potential?
Is it B, the sodium potassium pump?
B, the sodium potassium pump. Yes. What else do you have to have for the sodium potassium pump to constantly be pumping things against their concentration gradient?
ATP, so it would be D?
What about, yep, it'd be D. Correct. Questions? So signal conduction along an unmyelinated nerve fiber versus a myelinated nerve fibers. So think of myelin, remember that's essentially insulation around a wire. The wire meaning the axon. When the signal is conducted along an unmyelinated axon, there's voltage gated channels along the entire axon length. The entire axon length. In myelinated axons, voltage ion channels are scarce along the myelin-coated internodal regions. Remember the nodes of Ranvier, so the internodal regions are in between the nodes of Ranvier. So they're the ones that are covered by myelin. The regions of the axon covered by myelin are the internodal regions. In these internodal regions, there are fewer than 25 voltage gated channels per micrometer squared. However, at the nodes of Ranvier, or the gaps, there's 2,000 to 12,000 channels per micrometer squared. At unmyelinated axons where their voltage gated channels are the same along the entire axon length, the action potential occurs at the trigger zone. Sodium diffuses for a short distance along the plasma membrane. The resulting depolarization, remember that sodium diffusing out, the diffusing into the cell. The resulting depolarization opens voltage-gated ion channels immediately distal to where the action potential started. Remember that you still have the absolute refractory period, so it can only move one direction. Because of those refractory periods. So the resulting depolarization opens voltage-gated sodium ion channels immediately distal to the action potential. Both the sodium and the potassium channels open just as they did in the trigger zone, and a new action potential is produced. Just like we saw before. And the steps 1 through 3 occur until the end of the axon is reached. So as few sodium channels open, they open more. It keeps moving forward because it can't move back. We can't initiate an action potential back here because we have to wait for all the sodium channels to open, or excuse me, all the sodium channels to close before another action potential can be initiated. So it has to move one direction. And at each region, as minus 55 millivolts is reached, another action potential will be initiated. So this is the way a signal is conducted along unmyelinated nerve fibers. So the result is that there's this non-interrupted wave of excitation along the fiber called continuous conduction. This continuous conduction allows for repeated nerve signals to move along the entire length of the axon. And only the membrane ahead of the action potential is sensitive to initiation of action potentials because of the refractory periods that prevent the nerve signals from moving backwards. This looks kind of like a wave-like sequence where it never loses amplitude from beginning of the fiber to the end. Questions? In myelinated nerve fibers, rather than having a continuous initiation and self-propagation of action potentials, where they just keep occurring one after another, after another, after another. In myelinated nerve fibers, there's a saltatory conduction because voltage channels are scarce in the myelin-coated regions. There's no voltage channels here. So ions can't leak out in or out in this, where the region is coated with myelin. So sodium only enters at the nodes of Ranvier. Only enters at the nodes of Ranvier. You can't move backwards because of the refractory period, so it has to move forwards. So the positive charges of the sodium move fairly rapidly along this axon because they can't move out of the memory. So it moves fairly quickly along it. There's no leakage because of all that. Remember, we have all this insulation, so there's no leakage of charge here. As it enters the axon, each sodium has a positive charge around it, which gives it its own mini electrical field. So the sodium ions, when they're in the axon, they repel one another. Now positive charges, same charges repel. So they repel each other down the internodal regions. So the sodium may not move very far in these regions, but the electrical repulsion of each ion is going to result in an energy transfer along the axon memory. Remember, that's called the axolemma. I don't think I've ever, when I living here in the US, and I've ridden the subways a little bit around Washington, DC, but not very much. But I lived in Japan for a little while. And when I lived in Japan, those subways could get really, really crowded. And depending on what time of day, if you ride the subway in Japan, they have people who are hired to essentially push people pack more people into a subway car. So think of saltatory conduction as like a crowded subway car. The doors open and and this is like the sodium gates at each node opening. 20 people get on to enter into the car. Everyone has to be pushed to get to the rear of the car to make more room. So all the sodium gets pushed to make more room. No one passenger moves from the door to the rear, but the crowding and transfer of energy from one person to another forces those at the rear to move a little, like the ions being pushed to the next node. They're not all moving one direction, but they don't really have a choice. So they randomly get pushed towards one side because they can't move back. The events at one node thus create excitation at the next node, some distance away. Questions? Stay with me for just a few more minutes here. So the myelin in these myelinated nerve fibers are going to seal up because they prevent leaks. No way for the ions to move through all this myelin. So the ions are stuck in that membrane until they reach a node. They're stuck in that axon. So the higher concentration of sodium at the membrane causes the energy transfer to occur faster. Also, remember how sodium, the positive and the negative charges like to stick next to each other, even across the membrane. Negative and positive charges are attracted to one another. Well, because of the like 100 layers of myelin here, the charges outside and the charges inside are farther away from one another. So the sodium ions inside the axon are going to move freer, transferring more energy from one ion to another. They're not as bound to each other from the outside to the inside. So they move freer inside the axon. Questions? So this saltatory conduction, rather than having to self-propagate every second, it now only has to be propagated a few times rather than every other minute. It only has to be propagated at the nodes. And the majority of the axon is myelinated. So the conduction is really fast in the internodal regions. Conduction is slower at the nodes of Ranvier, but it's non-decremental because there's no leakage of ions. So conduction occurs fast in the expansive internodal regions, creating this excitation at each node. So when you're not having to continually propagate it, but you're only having to propagate it a few times, it's going to go a lot faster. You're not having to continually do it. It's now going to go a lot faster along the whole axon. If you're not constantly having to reinitiate it, it's going to occur a lot faster. An analogy is throwing the ball in basketball versus dribbling. Having one team member dribble the ball down the court to the basket or passing the ball is faster. Which is faster, passing it? The speed down an axon is determined by the myelination, the temperature, because temperature is always energy, and the diameter of the axon. The bigger the diameter, the more ability there is to move charge along. Let me do this real quick and we'll end right here. So looking at a general picture of an axon, input zone receives incoming signals from other neurons. So the dendrites and the cell body. The trigger zone initiates an action potential. The conducting zone is going to conduct action potentials in an undiminishing fashion along the long distances. The output zone is going to release neurotransmitter that influences other cells. questions? We will start right here next time. So we'll start at slide 100. We will finish this next week and we will start talking about the spinal cord, going into chapter 13. Have a good weekend, okay?
Thank you. You too.
Have a good weekend.
Have a good weekend.
You too.
Can I talk to you before we?
Yep.
So I am trying to make sure that, like, catch up on my work,
Uh-huh.
and